All right, so now we begin with today's lecture, and we want to review some of the principle behind the proofs. And before I move on, so these principles are taught in Math 415, and they are very simple. I just want to refresh your memory, okay, and maybe help you to understand more complicated proof, because from now on we're working on proof for 547. So those proofs are more complicated, okay? All right. All right, so what is called a mathematical? So first, when we talk about proof, we want to talk about mathematical statement. Okay, so a mathematical statement is a implication statement. So we talk about it. We talk about this in 415. So P imply Q. So P is a hypothesis or assumption, and the Q is the conclusion. So this is the logic structure for a mathematical statement. Okay. Now, give an example like if you have a statement like this. So this is a typical problem we talk about in 415. So the statement is like this: if A and B are real, then A squared plus B squared is greater or equal than 2AB. Okay, so this statement, so you can see that there's two things. One is a statement. There are basically two statements linked by if and then. The first one is called the assumption. A and B are real, so this is an assumption. And then you have a conclusion. So this statement is an implication statement. It means that we want to go from the assumption to get conclusion. Now, how do you get that? How do you get this? Basically, to prove this, it means that you have to find intermediate statement between assumption and conclusion in a logic way. So this means that proving it is to look for true middle statement, P1, P2, so on, begin with assumption. Okay, A and B are real, then this will imply P1, will imply P2, and so on. Finally, you can reach to the conclusion. So that's the structure. So proving a statement is like it's basically finding the middle statement, and those arrow between this statement, there's arrow. So this arrow basically like from assumption to P1. So this is a true statement, true implication statement. Then P1 to P2 is also true, and P2 to P3 is also true, and so on. So it's like they linked a number of implication statements together. So you can go from the assumption to the conclusion. So that's called the mathematical proof. Okay. So what we're trying to do is today I'm going to use this principle to revisit the one we proved in the, basically the theorem 1.5. Okay. Well, of course, the theorem 1.5 is more complicated than this. And this problem in 415, we know how to do it. It takes only 2 steps to finish the proof. Okay. So let's revisit 1.5. So 1.5 means that we're going to show that U is a supremum. U is the least upper bounds. It's equivalent to the property 1, property 2. That's 1 means that there's no S satisfied this. And the property 2 say that if V less than U, then the following will happen. So we're going to revisit this proof, okay? So because it's if and only if, so therefore you have the proof involve 2 parts. The first part is actually go from the fact that U is a supremum. So this is an assumption, okay? And then you want to see that, and this will imply property 1, property 2, okay? So in this direction. Now, because we'll go from this assumption to 2 things, property 1, another thing is probably 2, so therefore the proof is basically divides into 2 paragraphs. Now look at the first one, proving the property 1, okay? I think you have reviewed the detailed proof because you have a homework problem, right? Okay, so you understand all the detail here. here I just want to indicate in the first paragraph, where is the statement here? That's here is a statement, okay? Now, those statement is printed in red. So first one is U is upper bound. This is basically it's assumption, because we know that U is a supremum. So U is a supremum is involved two things, saying that U is the upper bound and also U is the least upper bound. So by saying that U is the upper bound, so this means that you are using the assumption, okay? And then from the assumption, you go to the next statement is S less or equal than U for all S. So this is basically follow the definition. So what exactly mean by U is upper bound? And this is what you mean by U is upper bound. For every S, for all S in S, S is less or equal than U, right? So naturally, by definition, you go from assumption to a P1, that's the middle statement. And then thus is connecting words for connecting the second statement. So there's no S in S such that U is less than S. So this is basically a restatement of the assumption. And it's equivalent to the previous statement. So therefore, it's a simple thing. Now, once you get there, so this proves the property one. So from assumption to property one is very simple. It's involved these few statements, that's it. Okay. And later, in a moment, I'm going to show you the logic flow. Excuse me? Any questions? Okay, so now let's look at the second paragraph. Second paragraph is basically you go from your assumption and you want to continue to prove the property 2. Okay. And here you can see that the writing is more complicated. So what is first statement? I mean, the assumption is U is a supremum, right? Okay, and from this assumption, you will get the first statement. This first statement is mean let any V less than U, then V is not an upper bound. The middle writing, I mean, then things will, so this is, I'm repeating, I'm giving the reason. Okay, the reason allow you to go from the assumption to this statement. So the real statement is let V less than U, and then V is not an upper bound. Now, why this is true? Because I know that the U is supremum. Being a supremum, this means that the U is the least upper bound. Okay, so this means that for any V smaller than U, then this V cannot be an upper bound. Now, because of this, so by the definition again, you get the first next statement. There is a S sub V, such that V is less than S sub V. This is just because follow the fact that V is not an upper bound. So this proves the part 2. Okay, so if you look at all these statements, so you can see the proof is basically formed by the statement and also connected by some linking words, some connection words. Okay. So the reason I want to show this is because I want you to think about it more logically. Okay. So when you have when you see a more complicated proof, and you always want to go back to the logic flow to see and how the logic is involved here. Now I'll show you the flow. Okay, so now we have a big assumption. U is the supremum. So what does it mean is U is the least upper bound, right? So here in this assumption, okay, you basically assume the two things. First thing is U is upper bound. Another thing is U is the least upper bound. So when we prove the property 1, property 2, we use both assumptions, both parts, okay? For instance, now I'm going to show you the flow to the property 1. So from the fact that U is the upper bound, we're not using least yet, just using the fact that U is the upper bound. This implies that, I mean, this is just a definition, what I mean by upper bound, right? So S less than equal to U for S. And from here, then you continue the next statement. Then this will imply there's no S such that U is greater, U is less than S. So this statement is basically, it's a statement of the previous one in a different angle. So that's equivalent. So naturally you go directly to get this statement. And then once you get this statement, actually you get the probability 1. All right. And the other side, to get a probability 2, now you are using the fact that U is the least upper bound. So you're now focusing on the fact that U is the least one. Since U is the least one, so this means that for any V, smaller V cannot be upper bound. Okay, so therefore, this will tell us that there is a S sub V. There's a S sub V such that V is less than S sub V. And this is just the probability 2. So you can see the proof of this statement is still very simple. It's only involve a few steps. Okay, here, what I want you to see is the logic flow. You gotta be very clear about this, okay? So this is one direction, showing you that U is the least upper bound. From the fact that U is the least upper bound, you can get that probability 1 and also probability 2. And then you have to go the other way. So assuming probability 1 and 2, you want to show that U is the supremum, okay? And so this way, I mean, the proof is slightly different. And now here is the proof I given last time, right? And also involve 2 parts. And as you can see for a moment about logic flow, why we need these 2 parts, you can see clearly. Now look at the first part. The first part basically starting 1 is the assumption, okay? 1 is the probability number 1. So you have 2 assumptions, probability 1 and probability 2. Now first I use the probability 1 assumption. And this will imply a statement. I mean, what directly imply that for every S less than for every S is less than or equal than U. So this, then you can immediately say that U is upper bound. Okay, so this, so you use probability 1, you get this. And then you use probability 2. And probability 2 will imply that, I mean, look at the probability 2. So this means that for every number, smaller number V, then V cannot be upper bound. Okay, this follows from the probability 2. So this will finally imply that the U is the least upper bound. Okay, so that's the second direction, the sufficient part. Okay, so again, the sufficient part is kind of interesting. So let's again revisit the logic flow. So in the logic flow, I begin with probability 1. Okay, I have 2 probability. Okay, probability 1, probability 2, both are assumption. So from the probability 1, I can get that S less than U for all S, right? And so therefore, this will imply that U is upper bound. Okay. And so that's a partial result. It's not enough yet because we want to show that U is the supremum. So we want to show that U is least upper bound. So the least things is missing here. We haven't achieved that. What we achieve here is U is upper bound. That's it. So to show that U is the least upper bound, now we go to the probability 2. So that's the second piece of the assumption. So probability number 2. So now we'll begin with second paragraph. Okay, so the probability 2 implies that, I mean, the implication from probability 2 is pretty simple. This implies directly that for every V less than U, U will not be upper bound. That follows from probability 2. Okay, so from both probability 1 and probability 2, we get some partial result. Now, if I patch these 2 partial results together, you can get the final result. U is the least upper bound. Because probability 1 will tell us that U is upper bound. And the probability 2 will tell us U has to be the least one. So therefore, U is the least upper bound. So that's the logic flow. Okay. So analyzing a proof using logic flow belong to 547. 415 class, okay? It's not belong to this class. But here I'm using this will help you at the very beginning. And I guess maybe you can learn how to analyze using logic flow by yourself for every proof. Okay. Okay, so this is the proof of 1.5. Now, as I said that I assigned a whole problem, 1.6. Now, because of this, I analyzed so much of 1.5. I don't think you will have any problem with 1.6. Okay, the proof is just parallel. Okay, so I don't need to spend time on this. But instead, I want to look further. I mean, some other homework, the problem number 2 and number 3. So the homework problem number 2 and 3 will be assigned today. But here, I want to do some analysis with you. I don't know whether you have taken a look at, get a chance to take a look at problem number 2 or 3 yet. Now, homework problem number 2 means this, okay? It says that if a subset S contains an upper bound, okay, so that's the assumption. And from this assumption, you want to show that this upper bound has to be the supremum of S. Okay, it starts with the upper bound, but with some special property. I mean, when you talk about upper bound is controlling the whole set on the right side, right? The upper bound itself may not belong to S. For instance, you think about interval 0, 1, open interval 0, 1. Any upper bound of this interval, okay, it's not belonging to the interval 0, 1 because it's open, okay? Now, if you have a closed on the right side, then you get the 1 upper bound which belongs to the interval itself, right? But here, general case is suppose you have an upper bound. It turns out that this upper bound belongs to SSL. Then automatically, this upper bound has to be the supremum of S. Okay, that's the thing you need to prove. Okay, so what is the idea here? The idea is trying to show that any other upper bound, okay, is always greater than or equal to this upper bound. That's it. I can tell you that the proof is very simple. It's just it's a one sentence or 1 or 2 sentences will finish the proof. Basically, it's followed from the definition of upper bound. Okay, I want you to think about it by yourself. Okay, so this is the homework problem number 2 is very simple, and problem number 3 is also simple. Problem number 3 is saying that suppose you have a bounded set in R. Okay, a bounded set. Well, what I'm saying is why I'm assuming this is a bounded set. Well, we are going to define what I mean by boundedness later in another place. But bounded set is that this set is bounded below and bounded above. Okay, that's it. Then you think about the S naught. S naught is a non-empty subset of S. Okay, so you have an S is a big set, then you have a subset of S. And then for both sets, you can talk about infimum and supremum, right? And then these infimum, supremum automatically satisfy these inequalities. And this is the things you want to prove. The assumption is very simple. You have a subset. And the conclusion is that these supremum, infimum should satisfy these inequalities. So that's the things we need to prove. But it turns out to be very simple. Again, I draw you a picture like this. You can see there's 2 sets. Okay, the one is behind it's the light, you can call light blue set, this slightly bigger one. The next one is a little bit dark blue. Okay, it's a subset, right? Okay, you can see that I used the red bar to denote the infimum and supremum. And I used the green bar to denote the infimum and supremum for the smaller set as dots. Then you can, from here, you can immediately see that excuse me, the infimum of the subset is always greater than or equal to the infimum of the set itself. Okay, obviously, so from picture, it's true. And the supremum will decrease instead of increase, or decrease. That means supremum of the subset will be less or equal than supremum of the original set. Now, in order to write down this proof, so the argument, the fact is actually very simple. Now, there are three inequalities here, but you have to pay attention to the middle one. The middle inequality is trivial, so you don't need to prove it. I mean, it's trivial. That means infimum of S naught is less or equal than supremum of S naught. This is obvious because for any set, the infimum is always less equal than the supremum. This is true. So what you really need to prove is the first inequality and the third inequality. I mean, you want to show that infimum of S is less or equal than infimum of S naught. And in a similar way, you can show that the supremum of S naught is less or equal than supremum of S. Now the thing is how you can write down the proof, write down this proof. I'll give you some partial hint, okay? So suppose I want to prove the first inequality. I want to show that the supremum of S is less or equal than, infimum of S is less or equal than infimum of S naught, okay? So I'm going to sketch some of the steps. Okay, now here, now you read it like this. So since X naught belongs to S, so this is a subset, right? So infimum of S, okay, now you talk about infimum of S, is less or equal than S for any S in S naught. Think about this statement. Okay, since we know that infimum of S is less or equal than S for any S in S itself, but however, S naught is inside the S, so therefore automatically this is true for S naught. Okay, so this is the first thing you write here. And then you can see that the infimum S will become a lower bound of S naught because infimum of S is less than any element in S naught, right? It's become a lower bound, but it not necessarily become the greatest lower bound. It has to be a lower bound, okay? And then you can see this will immediately give you that infimum of S is less or equal to infimum of S naught because infimum of S naught is the greatest one. And here we're getting one of the lower bound, which is infimum of S. Obviously, this infimum of S, this lower bound is less or equal to the greatest one. So that can be considered as an argument to prove the first inequality. You begin with the assumption, and you finally reach the conclusion. Okay. Now, there may be a multiple way to do that, but this is just one way. In a similar way, you can handle the third inequality. Okay. For the middle inequality, you only need to say that this is obvious. Okay. So you can spend some time to think about this. The proof, the writing of proof of this, okay? Maybe we'll come back to this problem next week about some logic flows, if necessary. Okay. All right, any questions? If no questions, then we'll begin today. We'll talk about today's, we'll want to make some progress on further theorem, okay? Okay, so today we're going to look at the applications. And last time we talked about the 1.5, right? It's a lemma, basically it's a result. Here we're going to see how we can use this result and to prove something else. Okay. So here the first thing we want to talk about is Archimedean proof, Archimedean theorem. Now the theorem, the statement of theorem, if you look at the theorem, you will see that the statement is silly. Why we need to prove things like this, okay? So what is statement? Statement is saying that if X in R, so here we're given a real number X, any real number X. The statement is saying that for any given X, there is always a natural number, which is called N sub X, such that X less than NX. This is obvious, right? Because for instance, suppose you give x equal 10.7. 10.7 is a real number. Then I know that this 10.7 is less than 11, less than 12, less than 13. There are lots of natural numbers satisfy this, obviously. Okay. The reason we are going to look at this is that because we're building the logic. It's a analysis. So we're starting with, that's the background. I mean, the basic fact. So still, we can use this basic fact to prove some of the result. So this result seems to me, seems to you probably, is a very simple. But however, if you want to prove this, then there is a way. You can go from the supremum property to do that. Okay, so this is the first application. We'll talk about the Archimedean theorem. Okay. Now, how we can prove this theorem? The proof is very simple. Okay, but here we are trying to so here's the picture. You can look at the picture. So if you give an x, and you can see those dots stands for natural numbers. So no matter what x is, you can always see some other dots behind this on the right side of that, right? Side of this. So what we need to prove, so what is the main thing we want to prove here? Okay, how we can reach this? We want to actually use the method of contradiction. And this is something we talk about in the 415, right? Now, using method of contradiction, it means that you assume the opposite. You assume the opposite of your conclusion. Then together with your assumption, you're trying to get a contradiction, okay? Now, what is the opposite of this statement here? The conclusion of this statement is being that there is a natural number xx such that x is less than nx, right? Now, the opposite of this is meaning that there's no such n sub x exists. What does it mean by no such nx exists? This simply says that the whole n, the whole natural number set, will be bounded from above by x. Okay, so this means that there's no natural number on the right side of x. So this means that all the natural number, okay, are on the left side of x. So in order to use the method of contradiction, this is our starting point. It looks silly, okay, but we're going to see that this silly starting point will lead to a contradiction, clear contradiction, okay. Okay, so now let's see that. So if you draw another picture, so this means that if you assume this, okay, you can see that x is upper bound of the entire natural number set. Okay. Now here we want to get some idea how we can proceed in the next step. Now here's the situation. The whole n is a subset. You can think about n as a subset, okay, on R, inside R, okay? This is a subset. And now, using method of contradiction, you first assume that the whole n is bounded by x. So x become a bound, is a special upper bound, okay? Upper bound. Then we know the supremum property, right? So the supreme probability will tell us that once a set has an upper bound, that this set will have the least upper bound. Okay, so apply this principle here. So we know that n is bounded already by x. It's bounded above. So this means that the n now is going to have a least upper bound. And that's the next step. We want to use this and trying to get a contradiction. All right. Okay, so now let's try to prove it. So we use the method of contradiction, okay? Suppose there's no such n. Suppose there's no xn. So this means that x is upper bound of n, okay? And so therefore, you buy the supremum properties. Now here we use this principle, using the supremum properties. So you can see that there exists the least upper bound for n. So that's the supremum property, okay? Now, why this is useful? Okay, so let's look at the next step. So this simply means that n is less or equal than u for all the n in n. Okay, so that means for every natural number, all the natural number is less or equal than u, and u is the least one, least upper bound. Okay, now this inequality will certainly satisfy with the fact that u is upper bound. For any upper bound, this is true, right? But however, in order to get the contradiction, here we have to use the least one in order to see a contradiction. Okay, so that's why we have to use a supremum property. The supremum property will guarantee the existence of the least upper bound. Okay, without using the least upper bound, then you cannot continue with the proof. Okay, this inequality will lead you to nothing. Only when you use the least upper bound will lead you a contradiction. Okay, now let's see the next step. So how we can get the contradiction. Now u is the least upper bound. So what does it mean? Is it this means that if you decrease the u for a certain amount, then the new u is not going to be upper bound because u is the upper bound, right? So in particularly, you think about u minus 1. U minus 1 is smaller than u. So as I said, any smaller than u cannot be upper bound. So therefore, u minus 1 is not the upper bound. Okay. Now, what I mean by u is not an upper bound? Okay, now it's come to what? Come to definition. You can think about the definition, or you can use the theorem 1.5. Okay, so there must be some integer in n such that u minus 1 is less than m. Okay, so this is what I mean by something is not upper bound. This means that you can always pick something from the set S, which is greater than this number. Now our S here is the whole number set. So therefore, you can always find m in n such that this m is greater than u minus 1. Okay, so this is going to give us a contradiction because if you look at this inequality, now the inequality on the left side you have minus 1, right? So I'm adding 1 to both sides of this inequality, you'll get to this. I mean, now u is less than m plus 1. But this here, I wrote that n plus 1 belongs to n. So this steps deliver two messages. The first message is that n plus 1 is greater than u. So that's one thing. Another second message is that n plus 1 is an integer. So the key point is the second message is tell you that now you're getting an integer in n, turns out to be greater than u. And this is not allowed based on our previous assumption, because previous assumption is saying that for any, I mean, the whole natural number set is smaller than u. And now you can see that you got an integer, which is turned out to be greater than u. Obviously, this shows that you cannot be an upper bound. So that will be a contradiction. Okay. So that's the proof of this result. Is any okay, so I see a question. Why would n plus 1 be a natural number if u is the least upper bound? Okay, u is the least upper bound. What implies that, okay, we're going to talk about this. So first one, why n plus 1 will be a natural number? Because this is because that m is a natural number. Okay, so you can see that there is a natural number m, okay, such that u minus 1 less than m, right? So if you add the m by 1, it still be a natural number. Like m equal to 100. You add a number 1 to it, you get 100, and 1 is still a natural number. Okay. And so that's why how you get a contradiction. And this thing actually is closely related to the fact that u is the least upper bound. Okay, because u is the least upper bound, so the trick of the proof is that u minus 1 is not an upper bound. Well, then u minus 1 is not upper bound, this fact will imply the existence of m such that u minus 1 is less than m. So then you will get a contradiction. I mean, from here you get u is less than m plus 1. That's what will give you a contradiction. So the key is that you begin with the fact that u is upper bound, u is the least upper bound, okay? Then you reduce u by something, okay, to get the next step, right? But the things you reduce has to be, I mean, you get u minus 1, okay? You reduce to u minus 1. So you can see, then you can see that you will eventually get n plus 1, right? Now, if you're allowed to reduce to anything smaller than u. For instance, you can reduce, say, well, since u is the least upper bound, so therefore u minus 1/2. Suppose instead of using u, I use 1/2. Then u minus 1/2 is not upper bound, okay? And it can still works, but in the end, what result you can conclude from there? You can conclude u is less than m plus 1/2. Then this is not going to give you a contradiction because m plus 1/2 is not an integer. Okay, you know to get you know what I'm talking about. So you want here. This is the reason why I'm subtract 1 instead. You can subtract 2. It also works. Okay, if you subtract 2, you will get m plus 2. It still works because it's still the integer. All right. Any other questions? This proof is very simple, but it's worth to think about it because the idea so once you get this upper bound and you reduce this by 1, okay, then this will create a contradiction in the end. Okay. Okay. Any questions? If no question, then I can continue. So this is the first theorem, the Archimedean theorem. Okay, it follows from the assumption, or follows from the theorem 1.5. Okay. So let's see. I will continue from here sometime. Okay. Then there's a further assumption, a further application. Okay, corollary. So this is some other result. Now here 1.8 is just consequence of 1.7. You can see that it's very simple. So here the assumption is that suppose you have x and y. Okay, so both x and y are strictly positive real number. Okay, strictly positive real number. Okay. All right. So nothing else. Okay. Then there's a conclusion. 3 conclusion. So first, there is a natural number n such that n times y is greater than x. Now, if you look at this statement, how do you think this one is related to the previous one? Okay. So the previous one tells us for any x, for any real number, if you pick any number x, okay, you can always find an integer n greater than that number, right? But this time, it's similar to that, but however, the inequality is very different. But however, you can see that this result can be reduced to the previous result, that is 1.7, Archimedean theorem. Why? The proof is just a sentence, okay? So by theorem 1.5, now you consider, the idea you consider x divided by y. Now x divided by y is a real number, okay? So by the 1.7, you can see that there is an integer n such that x divided by y is less than n. Okay, you just apply the 1.7 to a special case. The x is now replaced by x by y. Okay. Now, once you get x divided by y is less than n, then this inequality will give you the inequality you want for the part A. Then you times y on both sides, you get this inequality. So you can see that this result, the part A, is an immediate consequence of the 1.7. Okay. And part B says that there is a natural number n such that Okay, so now here x is arbitrary x, okay, arbitrary number. 1 over n is between 0 and x. So this means that no matter how small the gap is between 0 and x, and there always be a fraction like this in between. Okay. And this can also be reduced to the 1.7 because that by 1.7 there's n. So you think about you apply 1 over x instead of x in the 1.7. Then you can see for this 1 over x, okay, you can always find the natural number n is greater than this. So you get 1 over x is less than n, follows from 1.7. And then this inequality will become, I mean, you divide by n on both sides, times the x on both sides, you'll get this. Okay, the 1 over n is greater than 0 is obvious because this we're talking about the positive number. Okay, so this is the part B is also is a consequence of 1.7. Now part C is a little bit different. Part C is saying that there is a natural number n is controlling x. So x is greater than or equal to n minus 1, but less than n. You want to reach this. And this can also be reduced to the 1.7. The reason is because that by 0 and 1.7, there's always an n such that x is less than n, right? It's given. So that's exactly the 1.7. Now, 1.7 say that the existence of such n, a natural number n, to make this happen, right? And now, maybe there's lots of n. Obviously, there's lots of n. For instance, x equal to 1.5 is a real number 1.5. Then you can choose n equal to 2, n equal to 3, 7, 10, any number higher than 1.5 will works, right? But here, in order to reach our goal in part C, now we are going to choose, we can assume that n is the least integer to satisfy this. Okay. So what does it mean is that the 1.7 tell you the existence of this n, and this n may not be the least one. But however, you can always reduce this n one by one. Now, suppose you got n here, and then you can, n may not be the least one. Then you replace n by n minus 1. Okay. If n minus 1 is less or equal to x, so this means n is the least one. Otherwise, you can continue this process. You can replace by n minus 2 and so on. So because n is finite number, so therefore it takes only a finite number of steps to achieve the least integer n here. So that's why we can assume that n is the least integer. This means that you can always replace n by small integer, okay? And to get to the least integer here. Now, once you get the least integer n, okay, then n minus 1 has to be less than or equal to x. So immediately you get that's the result. So this result, the part C, basically saying it relies on 1.7 in certain way, saying that once you get n, then you reduce the n to the least one, okay? Then that n will satisfy this condition in part C. So this is the proof of the part C. So this proof A and B and C, they are basically just the application of 1.7. They're very simple. Okay, any questions? So they are simple stuff, right? Okay, so I'm not going to continue with a lot of stuff. Maybe we don't have to spend the whole class to talk about these things, okay? And I will say that the next one is a long proof, okay? Remember in the last lecture, we talked about square root 3 things, right? And here, the next one is not related to square root 3. Instead, it's related to square root 2, but it's follow the same argument. So from the math 415, okay, we know that square root 2. So this number, if this number exists, then the square root 2, this number is not irrational, right? It has to be irrational. But in 415, we never give a proof of the existence of square root 2. Okay, so here in 1.9, now using supremum property, so now we are able to prove the existence square root 2. Okay, so you can see that here where the supremum property will give us the real number theory, right? But here in this class, I'm not going to teach you the entire theory, but instead I'm going to teach you in some special case, the supremum property can be used to prove the existence of certain irrational number, especially like square root 2, square root 3, things like this. Okay. So 1.9 is a theorem which shows you the existence of square root 2. Now in the homework, there's a parallel result saying that the square root 3, they talk about the existence of square root 3. So once you understand the proof for the existence of square root 2, you should be able to write the proof for the existence for the square root 3, which is assigned to be maybe. So today I'm not going to finish the entire proof of 1.9, okay? But after we prove 1.9, then you can think about how to write the proof of square root 3. Okay, I want to make sure that so you are still comfortable at this stage. Okay, so I can tell you a little bit about the ideas how to prove this the existence of square root 3. Okay, so the approach to prove the existence is very, very special. So this is a long proof, and so we have to be very careful. Today, I'm going to just introduce a little bit about this idea. I'm going to leave the proof, okay, the major portion of the proof into the next lecture. So what mean by we want to prove existence square root 2? So this means that we want to prove the following. We want to show that there is a positive number x in R, such that x squared equal to 2. Any solution to x squared equal to 2 is a definition for square root 2. Okay, so well, this equation have two solutions. One is positive solution, the other one negative one, right? So here, let's just talk about positive one. So okay, we want to show that there is a positive number x to make this happen. Okay, now let's say a few words about the approach. Okay, the approach is that at the initial stage, let's define a set. It's called S. Now this set is defined to be, now here are notation using set notation to define this set. We'll talk about a collection of all the real number such that x squared is less than or equal to 2. I just define the set. The reason I'm defining this set is that you cannot immediately prove the existence of square root 2. I mean equal sign, right? But however, instead of using equal sign, now using less than equal to, then you can see there's a lot of numbers set by this. For instance, x equals 0 satisfied, x equals 1 satisfied this, right? They're all satisfied. Okay, so S is not a, S, the set is defined this inequality, okay? It's not an empty set. It's a non-empty set, okay? If we have a non-empty set, then we can work on this, okay? Okay, now first, when I have this set, now first, since I want to go from here, continue, I want to understand a little bit more about this set, okay? So for instance, whether this set is bounded or not, whether this is a bounded set, okay? So the first thing we want to show is that S is bounded above Fs, of course, and S is also bounded below, but I'm not using the second one. So I just using the fact that S is bounded above, okay? Now, how do you prove that S is bounded above? So this means that I want to find a number, control all X in this set S, okay? So how can we come up with this number? Okay, now there's a very simple argument. Now you take an X in S, okay? Then you look at this fact, X squared should be less or equal than 2, right? That's a definition of S. Then 2 is less than 4. So this means that for every x in S, x squared is less than 4. And now you take a square root on both sides. If you take a square root on both sides, you will immediately get that for every x in S, S is less than 2. So this means what? 2 is the upper bound of S. So this is how we prove that the set S is bounded above. Okay. And in a similar way, you can show it bounded below, but we don't need that. We only need the upper bound. Okay. Now you have that the S is a set which is bounded above. Now at this point, I can apply the supremum property. So supremum property say that for any set which is bounded above, you can always find the least upper bound. The least upper bound always exists. Okay, so apply this principle to here. Now S is a set which is bounded above. And then this means that by supremum property, S has the least upper bound. Okay, so let's just denote this least upper bound by S. It's just a notation. Okay, so that's a major step using supremum property, showing that there's a least upper bound for this S. And then I state the goal of the proof. We want to show that this least upper bound will actually provide the solution. That means S squared is exactly equal to, not less than. Okay, so you see the supremum property gives us existence of such S, little s, right? It's the least upper bound. In the next step, as a long step, and we want to show that actually this least upper bound turns out to be a solution. So this least upper bound is just a square root 2. That's it. Okay, so that's the idea of proof. Okay. Now here comes to some a way how to prove S squared equal to 2. So I have a S. Okay, S. I know that it is least upper bound. Okay. Now how do you show that S squared equal to 2? Okay, and you cannot reach this directly. So we have to use some indirect way to see this. Now here, what we're trying to do in the next step is we are trying to achieve this by showing that S squared is greater than or equal to 2, and also at the same time, S squared is less or equal than 2. Okay, so this means I want to divide the rest of the proof into 2 parts. In the first part, I want to show that S squared is actually no smaller than 2. Okay, and that means S squared is greater than or equal to 2. And in the second step, I want to show that S squared is less or equal to 2. Now, if I combine both, you can conclude that I can conclude that S squared equals 2, right? So that's the design of the proof in the next steps. Okay. So in the next proof, I want to divide it into 2 steps. First step, I want to show that S squared greater than or equal to 2. In the next step, I'm going to show that S squared is less or equal to 2. Okay. Now, first step, we want to show that S squared is greater than or equal to 2. Now, how to achieve this? And it turns out that it's very difficult to achieve this directly. That means you cannot use a direct proof to achieve this. Then we want to use some indirect proof, okay? Indirect proof, for instance, the contradiction method. So we want to prove using the contradiction method on part 1. Similarly, we also want to use contradiction method to the second step. Okay. So what you're going to do is, now let's assume that S squared is less than 2, strictly less than 2. And then from here, we're going to get a contradiction. Okay, now here comes a long story. I'm not going to continue today, but I'll tell you a little bit, and maybe you can think about this by yourself. So here's the situation. Now, we want to prove S squared is greater than or equal to 2, right? But I use the contradiction method. So using contradiction method, I assume that S squared is less than 2. Now, by assuming S squared is less than 2, from the graph, you can see that between X squared and 2, you can see there is a gap. Okay, there's a gap. This gap may be small, very small. You cannot measure it. I mean, by assuming S squared is less than 2, you're just saying that there is a gap between S squared and 2. S squared is on the left side of 2. Okay, that square, that gap will provide us a way to get a contradiction. Basically, we're trying to find n, maybe a large n, so that 1 over n added to s, okay, then square it, will still be less than 2. You see, s is there, okay? Then s plus this tiny number, 1 over n, will be very close to s. If I can choose n large enough, then you can see that the s plus 1 over n, then square, will still on the left side of 2. This is because there's a gap, okay? So this is something we want trying to get first, then before I can get a contradiction. So I cannot, so maybe next time we'll continue the proof. Okay, the proof is long, so I'm not going to do this, all the things today. All right, so this is all I have to say today, okay? Do you have any questions regarding the argument I'll present here? So the homework will be the homework problem number 2 and 3, and we just discussed these 2 homework already. So you're trying to work this out by yourself. All right? Any questions? If no questions, then we can finish here, and then in a moment, I'm going to start with the office hour. Oh, one thing I forgot to say is that for the homework, you don't have to turn in the homework, and we always want to discuss the homework together. And later, if necessary, I could provide this homework solution to you. Okay, so all these homework are important. So you have to prepare these things, and so for the chapter quiz. Okay.
Yep.
All right. So that's it for today. So okay, I see one question maybe. Do I have any question here? No, the homework will, what I mean by will homework be posted on Blackboard? No, actually the homework, you don't have to post it on the Blackboard, okay? You handle the homework by yourself, okay? And so maybe I will share the homework solution. I'm not going to share the homework solution on the Blackboard, but instead I'm going to share you some of the solution in the class. Okay.
Okay, thank you.
Okay, great. All right. Okay, so that's it for today. So after the class, I'm going to upload. I'm going to upload this the recording immediately to the YouTube. Okay, and you can check so maybe half an hour after half an hour you can see it's ready. All right. Okay. Good. See you next week. If you have questions, we can talk about during the office hour. All right.
Thank you.
Okay. Bye-bye.